Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm Sky, and I'm from machine learning group. So it's my pleasure to introduce Kira Rudinsky today to give the talk. So Kira is a researcher at Microsoft Innovation Labs in Israel, and also a PhD student at Technion University. Okay. So Kira has done very interesting work, and she's currently doing an internship here with Sue, right? With Sue and Eric. So today she's gonna teach us how to use today's news article to predict events that's gonna happen in the future.
Sure.
All right.
Okay, so hello everybody. So as I was introduced, my name is Kira. I'm from the Technion. I'm presenting here stuff I was doing during my PhD. So in this talk, I will cover a brief motivation for a problem, a bit of the problem definition, models, representation of events, and then I'm going to talk about the algorithms and results. So let's start about the motivation. So let's say we had Japan's earthquake not so long ago. And wouldn't it be cool that we had a system that can actually output, there's going to be an iPad shortage soon. Why? Well, why is it so cool? How is it connected? So it turns out that Toshiba is actually making their chips in Japan. And because of the earthquake, they were out of, I don't know, some kind of material. And based on that, we didn't have those chips for iPad 2. And this is why, well, when I was coming to buy my iPad 2, they didn't have it. Okay? So what was actually happening here? We only saw an event in the news of Japan earthquake. But we had to learn much more about that. We need to understand that based on that, there was some kind of damage to all the things that are inside Japan, right? Stuff like factories. We need to understand that one of those factories is actually Toshiba factory. We need to understand that Toshiba is actually selling things to Apple. We need to know that Apple is making iPads, right? And then the most important thing, we need to understand that if you don't have chips, you don't have iPads. Okay, so there are a few things we have to understand here. First of all, we need to understand all this type of reactions. So we need to know about the past. We need to see stuff that in the past, something that happened, let's say an earthquake, caused damage. And we need to understand what damage is. We need to understand that damage is actually making less income, less production in factories, and we have to have world knowledge about what type of factories you have in Japan. So this is the type of work I'm going to show you here. So the system is actually reading the entire news events that we have now and trying to actually give you future events that's going to happen. So let's say, given Japan earthquake event today, it's going to say something like iPad 2 shortage. It doesn't say when, but it knows that it's going to be caused. And it can give you how exactly it's going to be caused. It's going to say, OK, Toshiba is going to make less chips, meaning no iPads for you. OK, so let's start with this motivation. So a lot of people ask me, OK, what is prediction? What is it important? So first of all, for me, it was important because I want to buy my iPad 2, right? So I want to decide about this stuff. And prediction is not, magic. You don't have like a crystal ball, and you look inside, and you say, OK, so what's going to happen now? Well, you can make it actually a science. But the only thing you have to remember is you need specific conditions, and you have previous knowledge. So you need to know what caused something in the past, and you need to understand world knowledge, like, OK, damage, causes, problems in factories. You need to understand what damage is. And you need to see a lot of events which caused other events in the past. So not everything can be predicted. Japan earthquake maybe was not predicted. I don't know, maybe we didn't have the right features, we didn't see the right events. But it looks a bit random, right? But certain stuff, like ripple effects based on that, can actually be predicted if you see enough stuff in the past, enough training examples. OK, so again, well, why is it important if I didn't convince you yet? So I'm going to talk about money. Usually it's very useful to people. So let's see. Do anybody know a company named Recorded Future? Well, that's too bad because Google and CIA gave a lot of money to this company. So this company it's a software company in Cambridge, actually not the real Cambridge, the one in the States. So they're specializing in predictive analytics. Okay, they use what they call a temporal analytics engine. Okay, so actually they look at different events that were happening in the past and visualizing that and give you some kind of toolkits to try maybe to infer what's going to happen. Basically, they'll have documents, they do a little bit of entity extraction, looking at different entities with the same stuff, and saying, okay, based on these documents, this is what happened in the past. Okay. Another thing that was really interesting in last years, we see that Twitter can actually predict the stock market. How come? Okay, so if you feel the sentiment and you can actually know what people are feeling, you can maybe know whether it's going to go up or down. Because when people are happy, they buy more. When people are sad, they don't buy. When I'm sad, I don't buy iPads. Okay, or I'm sad when I don't buy the iPads. Okay. And another thing is, a lot of people talk about like how much something is mentioned, how much the stock is mentioned in Twitter. Is actually a good predictor of a stock market. How much do you think it is? Like, what's the precision? So there was a paper from Indiana, I think. It goes around 87%. Okay, so you say, okay, stock market is not predictable, but it turns out that stock market is actually affected by people, and people are predictive, right? Easily, well, not easily, but at least can be predicted, right? Again, because we have the same world knowledge, and we experience the same past, well, almost all of us. Okay, so let's go to something more formal and more, let's say, mathematical. So let EV be our set of events. And the prediction function that I'm trying actually to learn comes from a set of events that are actually happening today. So this is like the set of events. This is a certain time. And I'm actually trying to give you a set of events in the future. Why is this set? Because sometimes you have, let's say, correlation between different events. If something happens now, right, and a certain different event did not happen, maybe it's going to cause something else. Okay? So basically, this function is receiving several events today and a time, and the output would be a certain events that we think are going to happen after this time. That's it. This is how we define prediction. This is what we're going to get there. Well, hopefully. Okay. So, okay. So we want to talk about what is actually an event, right? So how do we define an event? So I'm not a philosopher, but there were a lot of philosophers who actually addressed this question. One of them is Kim. Kim was talking about an event as something that has objects, has some kind of property, which is what is happening to them at a time. So let's, for example, somebody is walking today, right? So the object would be somebody, and walking would be the property that someone has. And they were talking about how to actually structure that. But why do we want actually to model an event? Because eventually we want to get to something which is easily comparable, easily to generalize. Because if we see a certain event, right, and it never happened in the past, so what is the most human thing to do, right? So usually we try to generalize to something we have seen in the past. So if we don't have something which is canonical, it would be hard to do that. And of course, the last reason is reasoning. Okay, so the goal is actually to get from a certain event, let's say all the tags we have, how can we present it in a way that is actually comparable? So I talked about Kim that discussed it. Okay, so you need only, let's say, 3 features. Who did it, what was happening to him, the property, and when. And there's something really similar to that, well, in a certain different way. So Schenk was talking about how can the entire language be represented by, let's say, I think 11 set of verbs. Okay, so he's thinking like, okay, I want to say something to you, so I'm doing an M-trans of information from my mouth to your ear. The interesting thing about that is actually a generalization of a language into very small classes. Okay, so this is actually something that we can think about using. So maybe instead of using any action which is possible, we can get to a certain classes of actions and to model it. So let's get to our to our representation. So we look at events as something that has an actor. So let's say we have this sentence: U.S. Army bombs a weapon warehouse in Kabul with missiles. Well, not me, it's from the New York Times. Okay, so who did the action? In our case, it was the US Army. The action was bombing. To whom it was done, it is a weapon warehouse. And the location is Kabul. How it was done, this is the instrument with missiles. And when did it happen? This is the year. So I'm not going to talk exactly how we did it. I'm going to leave it for later. But think about it that you have lots of information looking like that. Okay, so it's like, say, 5 tuple in time. Okay, and everything you have is this. The next thing is, okay, so we know how event looks like. What is causality is actually? Right? So let's think about something like that. Think about it that a lot of people said this event causes this event. Okay? On every possible event. Well, not possible, well, at least the ones that were happening in the past. So for example, this one caused 5 Afghan troops were killed. And again, it's modeled in the same way. The question is, how do we get all those examples? So I'm going to give you like a hint before I dive into those stuff. So we crawled all the news from the 1800s till today. They did deep semantic analysis on those and extracted from the titles events that cause other events. So actually, think about it like that. If somebody says, 5 Afghan troops killed after US Army bombs a weapon warehouse in Kabul with missiles, well, maybe something shorter, right? So you can actually extract a lot of information from that. First of all, you know that one event caused the other because it was just said, this was caused by this. It's almost human labeled. Actually, it is human labeled because somebody wrote it as a title. The only problem is how to structure that. So this is for later. But let's assume for now that we have this set of examples. Okay, so we know that we have now pairs of algorithms. And we now need to think about, we have pairs of cause and effect. And we now have to think about an algorithm of how exactly to do that. So let's take the machine learning approach. Okay, so we have a goal function, which let's do something very similar. It doesn't go from set of events to set of events. Let's do something much simpler. Something that goes from one event and says, what is it going to cause in the future? So how is it going to look like? It expects a lot of examples, right? So how does examples look like? It looks, in our case, it's pairs, cause, effect, cause, effect. Okay? But pairs that actually the cause is causes the effect. Okay? Notice that it's only positive examples. Okay? Nobody's going to tell you, at least in the news, well, this didn't cause that. Well, it's not an interesting news title. So that's going to be a challenge. It's going to be interesting how to overcome this challenge as well. And our goal is actually to produce some kind of function, which is a good approximation of this, let's say, best causality predictor function. Yes, of course.
What is the loss error functions that you're considering here?
Okay, so let's do something binary, happened or not happened.
So for G, how are you computing the accuracy?
So we don't have G. Nobody knows. Okay, so the accuracy, as I'm going to show it, I'm going to be only showing precision. So for every event, whether it happened or not, just an indicator function. There's hard to define a function because a loss function, for example, because if somebody says, the algorithm says somebody died in Kabul, but instead somebody died in somewhere next to Kabul, did it happen or not? So we're trying to do something much more basic than that, just saying whether it happened or not. Okay, so the algorithm is going to be divided as always to 2 phases. One would be the learning phase. When given all this information, it tries to build some model that gets some kind of event that's happening today and trying to infer what it's going to cause in the future. And a prediction phase, where actually it's getting those events and trying to infer. So just to talk about the structure of what I'm going to talk about, so I'm going to start with the learning phase. That actually it has to look at all the events it saw in the past and somehow generalize those. Why? Because unfortunately events that are happening today did not exactly occur in the same way as in the past. So let's give an example. Let's say today we have an earthquake in Japan. But in the past I never saw an earthquake in Japan, but I only saw an earthquake in Turkey, how do I know that Turkey and Japan are countries, are not very similar? How do I know that an earthquake in country causes something? Okay, and then let's say even after an earthquake in Turkey, Red Cross help was sent to Ankara. So even if you understand that it's the same, you cannot output Red Cross help sent to Ankara for an earthquake in Japan. You actually need to understand the connection between the cause and effect. This is what I call causality prediction rule generation. You need to understand that Red Cross help will be sent to capital of the country. And the prediction phase, when we're going to get it. So it's basically finding something similar in the past, generalizing or at least understanding and applying this rule you created, which understands the connection between the cause and effect. So let's dive in. Okay, so generalizing events. As we said, we have objects, we have actions, right? So we need to be able to generalize the objects and generalize the actions that all actually build an event. And after we know how to generalize objects and actions, we're going to talk about how to generalize the entire event. So how do we generalize objects? Let's say somebody actually said, and for every concept in the universe, gave you some information about it. Okay, so let's see. So I'm originally from Ukraine, so let's start actually from the Russian Federation. So let's see something about where I was born. So Russian Federation is in group Eastern Europe. Russian Federation is very close to China. Okay, their currency is ruble, and I don't know, their ISO 3 code is RUS. But how do you get all this information? So this is the information you kind of need to understand that Japan is a country, right? And that Turkey is a country as well. So here's where we use ontologies. Okay, so there were a lot of people sitting and saying, okay, this is it, this is it. Okay, so usually what I'm using here is called linked data project. So just to tell you what it is, so the most famous one is DBpedia. DBpedia is actually a structured version of Wikipedia. Give you some of the examples. DBpedia dataset describes more than 3.5 million things. This is what they call it. Out of which 1.67 million are classified in a consistent ontology. 500,000 people, 500,000 places, 100,000 music albums, films, whatever you can think of. But the nice thing, it's an RDF, so you can easily, query it. The next thing is, okay, so why only DBpedia? The only stuff in Wikipedia are interesting. So the linked data project is actually trying to understand how to take concepts, let's say, from Wikipedia and link them to other stuff. So they have things about geonames. So for every country, you're going to have where it is located, GIS coordinates. And you'll have things about music brains. Music brains is a data set that provide information about artists and music. But how do you connect all those? So this is what it's called linkage. So people sat and said, this is the same as here. So you have, let's say, a lot of things and data sets that were separately apart. And then somebody actually was trying to link those. So this was something that was done by people. So we're trying to use all those. So think about, like, let's say you have this event you have. Try to map it in ontology and use this ontology to generalize. So how would this generalization help us? So for example, we would know that Japan is a country. So things there for people who know and come from NLP. So they have WordNet, which is representation of the word ontology, thesaurus. They have World Factbook, countries, book mashup, DBLP biography, whatever you can think about. The entire human knowledge in one place. Okay, so we know how to generalize objects. Well, at least we're going to general idea of how to do that. The next thing is we have actions, right? U.S. bombed something. But what is bombing? So the first attempt to do that was, as I said, conceptual dependency theory. It's from the 72, and it was mapped into 11 classes. So let me give you an example. So if you want to say Bob hands his wedding ring to the jeweler, you will actually write it like that. Look how structured it is. So preterence is actually referring to a transfer of physical location. Some object moves from place to place, as in go or move. And ownership doesn't need to be transferred. You have possession. So let's see what happens here. You have a transfer from Bob, okay, to jeweler. Well, what is it transferring? It is the wedding ring, okay, and when? Now, present. Another way would be to take the sentence and take, let's say, M transfer. M transfer is more like transferring something which is more mental. It's like, I forgot something. Okay, so how do you forget something? So first of all, who's me? Okay, so the actor is John. Okay, so he forgot the wedding ring, jeweler, from LTM. It's let's say I think it's the memory. They have like transferring something from my mind to your mind. It's coming from one processing unit to another one. So, and you have two, I don't know where because I forgot, right? So you have a question mark the location and time in the past. But what's the problem? Okay, so actually mapping that is really hard. Coming from text to that was found to be hard at least. Okay. So the next attempt, and this is what we're actually using, it's more practical, is not to try to map it into only 11 classes. Let's try 270 classes. And this is something which is called 11 classes. So they assume, specifically them, I'm talking about VerbNet, which is a big repository of verbs and classes. It's hierarchical. So everybody can say this verb belongs to this class. And this is how it should look like. Okay, so for example, class hit has the verbs bang, bash, hit, kick. Okay, the interesting thing about that if you see a sentence and you have this knowledge, you can go from syntax straight to semantics. Okay, what do you mean? I need to know who's the actor. I don't care who's the subject of the sentence. So this is what it helped me do. It gives me a lot of, let's say, rules that people wrote going from syntax to semantics. But sometimes you cannot use it, especially as we're going to see in news titles. It's not exactly English. It's like very abbreviated English. Okay? But let's say some of the times when you can apply those, it's a very precise way of going from what says to actually semantics, understanding who did the action, to who it was done to, and by what. Think about like regular expressions.
But it's not like clustering words, right? Because it's context dependent. Like bang and bash,
yes.
Sometimes are synonyms, sometimes not.
True. So it gives you the context itself. So it says like, if it has this kind of context, this is the class it should be mapped to. The only thing I'm saying is sometimes hard to map it. But let's say we solve this problem, right? It can actually really help you to map into a class. And this, but why is it helpful? Because next time somebody, I don't know, not going to bomb something, if something going to kick it, I'm going to say, okay, but it's the same thing. It's going to have the same effect. Okay, so we know how to generalize objects. We have an ontology. We know how to generalize the actions. We have a verb ontology. So how we do it together? So let's take an example. Okay, hopefully you're going to see it. So let's see we have this past event of US Army bombs a weapon warehouse in Kabul with missiles. And present event is NATO strikes an army base in Baghdad. So you want to know that those are the same. So what do? You say, okay, US Army. Okay, what's US Army? Okay, US Army, it's a concept of United States Army, like a Wikipedia article, right? And so you know how to map it to this ontology, and you know, okay, this number is, I don't know, ID 5554. Okay, NATO is also like, let's say US Army is part of NATO. This would be the generalization. Next thing would be strikes and bombs. Okay, both of them are in class hit 1. Next time is theme, right? Military facility. So they strike an army base and those struck a warehouse. What did it all happen? Kabul. So let's generalize. Arab city. How do we know that? Because we have this ontology that says this is an Arab city.
How do you know which one to pick? Because it will also say this is a noun, this is a name, this is...
Oh, what are you talking about? Oh.
How do you know to pick Arab city and not any other things that Kabul is or Baghdad?
Wonderful question. Thank you for that. Okay, so let's say you have a lot of examples and you want to know how to exactly to generalize. But let's say I had a lot of examples of something, the United States is bombing an Arab city, right? So I have this ontology and I'm trying to actually cluster similar events into a similar place. Okay? So what I'm doing here is actually hierarchical clustering. And how exactly is it done? So I need some kind of distance metrics, right? So I need to understand that both of those events are actually similar so they can be in the same cluster. So I can get into your question. Okay? So let's say, look at the algorithm. Algorithm is taking, let's say, titles or actually structured events and saying, okay, those belong to the same cluster. And then clustering up and up. And it has some kind of, says, let's say, well, I'm not sure, they kind of look alike, and it has a cutoff at some point if it's too not similar. But the algorithm is clear. It's like a common way of clustering things. The only thing that matters is the distance metric. This is what's usually different in those clustering algorithms. Yes?
If you clearly know that there's a co-resolution problem on the events, why don't you just train a supervised algorithm to do the merging instead of hoping that hierarchical will restore the actual event?
What do you mean? It's not used for this purpose. So what I'm trying to actually do is understand that those events are similar and trying to understand the connection between the cause and effect. So
what does similar mean? I mean, do you assume that they're describing the same real-world event, or I mean, similarity is a very...
Okay, I want something which is, if you generalize, they come to the same node. Let's say if you, let's say go back. Okay, so, sorry. It's going the wrong direction. Okay, so if I could look at the ontology and look at the distance from this event to this event, I would say that those events are similar. Why am I interested? Because it's actually generalizing. It's saying that both of these are countries.
What if the abstraction produced the same presentation of two events, but they're actually totally different events?
So you have the wrong example, right? The algorithm makes a mistake. But it doesn't happen very commonly.
Okay, so we're doing unsupervised right now, right? We just define the distance metrics, yes, and then we do the clustering, and yes, whatever comes out, comes out.
It's a combination because you got the examples of cause and effect. And you have a way of generalizing.
How do you measure the quality of generalization?
Okay, so this is in the end. It's like it's evaluating the entire system. The quality of generalization is based on the ontology, right? So just how well the people are succeeding in doing it.
Separate attempt to actually see how good the generalizations are. You just do it.
So we were trying to ask people to show them our generalization patterns that we produced. And we got high precision on those. People were saying, oh, they make sense. So this is the best evaluation we can find, but if you have different ideas, I would be glad to hear. Because it's not a simple problem. Okay.
Question, sorry.
Yes.
In the second sentence, you have with missiles, and in the first, the top sentence, there's no instrument.
Yes.
How do you know when the arguments are necessary for similarity of the two events?
Currently, what I do is I just measure. I have no weight on certain stuff, and if it's missing, it's not coming inside a weight. But it's just mainly heuristic at this point. Okay, so we have a way of generalizing, or at least conceptually. Now, as I told, let's say, if I don't want to output for an earthquake in Japan that Red Cross help is going to be sent to Ankara, I need some kind of way to understand that there's a connection between the cause and effect. Okay, so I need to understand that it's capital of the country that was mentioned before. So what we're trying to do is actually learn a path in the ontology graph between the cause event and the effect event. Okay? And now is it done? It's basically, you have a structure of 5. Look for distances between every node here, from the actor, let's say, to the, I don't know, to the theme. Look for all these possible paths, but there's a lot of paths. So first of all, if you were talking about practically, you just have to limit it, because too much generalization or going for long distances is too far. But the most important thing is, because we have those clusters of similar events, in every cluster we can look about the strongest path we found. So if I don't know, you have a lot of times that the US is bombing some kind of country, you're going to say, oh, and this is the projection that happened, capital of. Okay? So for every cluster we have certain prediction rules or projection rules, all weighted. Okay? So for example, here the path would be, okay, going from troops to Afghan, and here Kabul is a country of this Afghanistan. So this would be the prediction rule. Just a nice visualization for that. Okay, so what do we have now? So we have a huge clustering. Okay, in every cluster you have the prediction rules that if you come to this cluster, you have to apply them. And now your goal is you're given a new event and you have to find the most specific example you saw in the past, because you don't want to overgeneralize. You want to get to, I don't know, the closest but still not too generalized thing you saw in the past, and then apply this prediction rule. So let's see how it happens.
Can you define the most specific?
Oh yeah, so this is, again, hard to define, right? So I'm going to try the algorithm. If it's not going to be clear, I'm going to try to repeat it. So let's say we have Baghdad bombing. And because we have this hierarchical clustering, you can actually go from up to down, from most general to most specific. Because general is like, I don't know, bombing a country, right? But then you can bombing an Arab country, bombing Iraq, right? So we actually try to do the same similarity measurement as I defined before, the distance between those two events in the ontology graph, and to try to find the most similar event. So let's say you go to the first one, the similarity is 0.2, and then you see open it children, and you see this is 0.7, this is 0.3. Okay, so you say, okay, this one is more similar, let's go further. So you continue doing that, okay? So let's say, again, you're opening all these children, and you see, okay, here in the 0.8, I have something more similar. Okay, I'm greedy, I'm going to continue doing that. Okay, so this is the best child I found here, and this is the best one I found here. And you stop when you see that those are less, well, not as similar to the event as their father. So this is the greedy algorithm to find, let's say, the most specific but not too generalized. So you go from up to down.
Why do you think that this distance metric will be actually very predictive? I mean, it seems like you're putting all your hope on that the distance metric will A, go get the similar events together, and B, will find the event in the past that's the actual, as the causal.
Okay, do you want to hear the mathematical explanation, because, or the intuition? Okay, so the intuition is basically saying that if they are close for people, as we see the world knowledge, right? So the algorithms should think about it as well. So it's actually trying to mimic the way we think.
But I mean, of the bazillion possible similarity measurements of graphs, you're choosing one and saying that this.
Oh, I didn't define the similarity on a graph. I just said that you have two structured events. Find the distance. You can define the distance metric inside, right, inside a graph. So the one we use, for example, in our work, we're trying to find something that has a lot of paths between one another, right? It's not going through very general concepts. Let's say if it's not like the most general one, let's say object.
So you're saying that for a given domain, you would always just find one that suits the domain?
Yes. Okay, but the general idea is find a distance metric. I'm suggesting one that is based on this ontology. I'm not saying how exactly to measure the distance. Well, the intuition I can give is find the shortest path, right? And try to find a path that goes not through two general events, or two general concepts, sorry. Okay? This is the only thing I'm giving. And now, because we said in every cluster you have this prediction rule, you just have to take this prediction rule and apply it on something new you see. So you have to say that take the effect, theme, attributes should be looking like that. So let's say take capital of and apply it on Japan. Okay, and this should be your prediction. So eventually it's going to say Red Cross help sent to capital of Japan. Okay, and now I'm going to tell you about the entire system. So I told you about the different algorithms, the different ideas behind it, and now I'm going to tell you specifically, let's drop over that, specifically what we did to make all this from theory to practice. So the first thing we said, okay, we need a lot of examples, cause and effect. So what can we do? So we took the entire New York Times corpus. It was hard work. You need to go a lot of examples. So we went to 1850, okay, and we brought all the news till today. And what was the problem there? A lot of OCR things. Some of them they did it. Some of them we had to fix. And then you have to say, okay, but I need only things that cause and effect. Okay, so how do we do that? So we prepared a huge list. Let's say, I wouldn't say huge, but a big list of what we say semantic patterns. So they would say, if it says something caused something, okay, so we actually take the sentence, we're going to extract the events from it and put a label, like this caused this. So examples of those are caused, after, because of. And why do I say semantic and not just syntax, right? I'm not just looking for this word, cause. Right, because sometimes, for example, train crashes as the electricity didn't work. But how do you differentiate between that and as well as? Or I had a lot of problems is lots of happiness after 2010. Well, 2010 is not an event. So you actually have to understand that if you have an actor in the first sentence, okay, or first part of the sentence. So this is what we call causality pattern classification. Then we have to do an event extract. Yes, sorry.
Did you do this within one sentence or across sentences?
Okay, so we worked on the news titles. So only one, yes, news titles. And I'm going to explain what I do with the article itself. So because extracting causality from the entire text is an even more difficult problem. But let's start even like with one sentence. So event extraction, I actually need to know who did the action, to who it was done to, etc. So what we're doing is applying dependency parsing. It gives us subject, etc. And if we have things like the verb itself, and we know from verbnet, we apply the entire semantic pattern. And because the news title is so structured, you can actually apply those heuristics. The only problem is the language is a bit different, because if you say 15 dead, you actually mean 50 people are dead. It's not English, right? But so we had to build a lot of transformation before even applying this dependency parsing. So going from this stage on, so I talked about this semantic role, labeling, going to the semantics phase, if we can actually make it. Normalization, okay. So sometimes you have, let's say, the verb, right? So explodes, we have to become explode. So there are several ways of doing that. For example, using WordNet to find the base forms of things. And the next thing is actually understanding that U.S. Army. So U.S. is actually can be a university of something of Sultan, right? Or United States. How do you know, right? Because both of them can match. And this is where the article comes in. So we use the article itself and the text inside to find the most similar thing in the concepts we had. Every concept is represented as a Wikipedia concept. So you can actually measure the distance, the semantic distance between the two concepts, between the article I currently have and what I have in the past. So we basically use bag of words, similarity. And this is the disambiguation we have. Okay, context inference. You have 15 dead after earthquake. Oh, 50 dead in Japan after earthquake. What did the earthquake happen? So everybody says, oh, okay, of course, in Japan. Right? How do you know that? Because it was said actually in the first sentence. So you need to build a lot of relation extraction, like understanding that if it was the location in the first sentence, it's actually the location in the second one if it's missing. Okay, I'm gonna not talk about state inference because of time shortage. And eventually what we ended up with, we had a causality graph. We have a structured event with a 5-tuple in time, connected with a 5-tuple in time, going around 300 million nodes, 1 billion edges, all constructed from 30 million news articles. Okay, all this was built, on 20 machines, which we paid our best money for. Okay, so let's talk about the evaluation part. Yes, of course.
Can you walk me through the algorithm again? So you said, okay, we have events, those are 5 tuples plus time, right? Then we define some random distance between them through the,
Not random, but
No, well, okay, the ontologies on things induce actually the ontology on the events, so we can define the distance, like weighted distance over all the graphs or something, right? We do the clustering of those events, hierarchical. Then actually you, like from
prediction rules for that predictions.
Yes, so then you also not only define the clustering, but also define the like generalized event that defines the cluster as well, right?
True.
And then, so new event happens, you find the most specific one, then what? Like, where's the causality part?
Oh, okay, so, I get it. Okay, so I'm gonna repeat quickly. So we have the clustering. Okay, so every similar event's in the same place. Every cluster is actually represented by an abstract event, which abstracts those events inside, and a prediction rule, which actually helps you generate the effect. Right? It says like 15 people gonna be dead in capital of country. Take this and apply it on the new event that got to this cluster.
So you find the most similar, and then you say yes or no.
No, I didn't say yes or no. It actually outputs the event. No. It's not a binary problem. It actually outputs an event. So let's say earthquake in Turkey and earthquake, I don't know, let's say Australia, right? So it finds the most similar and says, okay, this is most similar to this event because I saw that earthquake in country causes Red Cross help sent to capital of country. So the output of the algorithm would be Red Cross help sent to capital of Australia. Okay, and then it's going to output Red Cross help sent to Canberra. And this would be the output of the algorithm. And now we're going to talk about how do you evaluate that, because it gave you like a sentence, right? It generates the entire sentence. So you know what? Before maybe I continue to the evaluation, I'm going to show you the type of things this predicts. Okay, so don't look in the middle, okay? But let's take a look about the examples. So we take an event, let's say Al-Qaeda demands hostage exchange, okay? And the algorithm predicts a country will refuse the demand. Why? Because it saw in the past that lots of different countries refuse demand of terrorists. So this is the output it gives you. Okay, so we're gonna go through it like in 1 second. Okay, so evaluation. Okay, so first of all, the first step would be understanding that what it says in text, it's not what's actually happening. So there's a notion of text entailment. Okay, so text entailment is actually saying that humans reading this text T will infer that H, the hypothesis, is most likely true. So let's try to do something similar and call it event induction. Okay, we will call it text 1 induces T2 at time tau if T2 entails the hypothesis H and H is true at this future time. Okay, so this is what the first thing we did. Okay, we were asking people to mark events as we were giving them events, random events that we got from the news from 2010, and asking them, what do you think is going to happen? One human. Then we took a group of people and asked them, here's the prediction of our algorithm. We didn't say which one, and this is the prediction of the human. Which one looks more reasonable? Okay? And why is it important? Why? Because we want to see whether it's actually causality, not just, random events that it predicts. Okay? So the results for that are, I'm going to show you this one. Okay? So we were asking people to actually give rankings of how logical the prediction is. Okay? So most of the people for the things that our algorithm gave us 3 and 4. 3 and 4 are possible and extremely possible. And actually for the human prediction, they gave mostly like possible. So actually this is statistically significant. It says statistically significant, the things that we output are more logical to people than, let's say, a random human.
So what's the second goal here? So you actually ask some people to predict whether possible.
Yes, well, I asked one person who I didn't know. Okay, here's an event, and this is, tell me what's going to happen. Okay, then I asked another set of people, here's what the human, I didn't say which one's human, and this is something else, which I'm telling you it's the algorithm. Give me grades, rated. Well, what I did is, let's take a look at the examples. So, for example, I show the person, Al-Qaeda demands hostage exchange, and asking him, what's going to happen? So the human says, Al-Qaeda exchanges hostage. The algorithm says, a country will refuse the demand. So I'm showing 15 people, I'm showing them, Al-Qaeda exchanges hostage, or a country refuses the demand. I'm asking them, give me a number between 0 and 4, how logical do you think it's going to happen? Let's see what else. You have volcano erupts in Democratic Republic of Congo. Yes?
Wouldn't that just bias people towards accepting more vague answers? Like if I give you a very specific but logical prediction,
Yes.
and the computer gives me a much less specific prediction, then the less specific one is more likely to be true.
Yes, but I wouldn't say that those predictions were extremely vague. Okay, it said a country, it didn't say which country, right? And at some point, let's say, it actually gave me where the funeral is going to be held, right? So it says, for example, here, professor of Tehran University killed in bombing. Okay, so it says professor and funeral will be held, and actually it said, Tehran, right? So it's kind of hard to do that. And people says like, Tehran students remember slain professor memorial service. Well, it makes sense. The only thing, I'm not even saying that we're better than humans. I'm saying the fact that we're similar to what humans are saying is really nice. Yes?
But you only asked one person to give these
True.
judgments. Because like Al-Qaeda exchanges hostage, that's actually not grammatically correct even. I mean, that's not a great response.
Well, yeah. Well, we asked just, let's say, a random person, but true.
Right, but I mean, it's the
It was-
incorrect understanding. Even you would say Al-Qaeda receives a hostage in exchange, but it's Al-Qaeda is not the one.
Oh, we were
who does
actually
it.
giving them, let's say, those are, what you see here is automatically generated. Those words, well, we were asking people to give in a structured manner. Who did the action, to it was done to, etc. And what you see here, grammatically speaking, was automatically generated. So this is not exactly what the human wrote. It didn't write it by hand. We asked them, like, who did the action, to it was done to, similar to what the algorithm would give. Yes?
So you have an algorithm that will take something and generalize it through the ontologies and whatnot. If you were to run these predicted human events, like what the human is saying would happen through that
Yes.
through that generalization, do you think it would be significantly different than what the Pundit is guessing? Like, Al-Qaeda exchanges hostages and a country will refuse the demand. Those feel different. But do you think your generalization algorithm
Well,
would
what are you
overgeneralize
suggesting? You're
these?
suggesting taking the fact and trying to generalize that fact?
Yeah. So like these say like war will be waged, professor funeral will be held.
Yes.
And I guess this kind of clues in with bias too. As a reader, I would be more likely to pick something vague because, well, it's more likely to happen the more vague it is, right?
You know what? Let's do an even simple experiment. Let's see which one of those happens or not. Yeah, let's ask, let's say, a bunch of people and do the following experiment. We ask them, giving the event, cause and effect, did it happen in the news or not? Right? Let's do something as similar as that. And ask them to say how much happened and which one not. And these are the results. Okay, so unfortunately it was really hard to check whether something happened in the news or not, especially like, I don't know, a funeral somewhere, it's not always reported in the news. Okay, so we're asking people whether you're certain or highly certain it happened. And things that we're not certain about, we just throw away from the evaluation because people were not sure if it happened or not. I'm going to give you things that, okay, so first of all, the precision is around 60% for the algorithm, and the humans is only 40%.
But I mean, couldn't that be connected to the vagueness of the predictions that the algorithm gives? Like
Yes,
it gives a really
Okay,
vague
so
answer, so
you say you're trying to give, asking people to give like more vague answers?
I mean, just something like that to control for that. To me, kind of take that factor out of consideration, right?
Yeah, well, okay. That's a suggestion.
Okay, just curious. Sorry.
No, we didn't try that. But that's a reasonable thing to try as well. Yes?
So at the end of the day, if you're evaluating events that happened in the past, you know what happened after, why don't you just evaluate against the actual outcomes?
Great question. This is what happened. I actually checking whether this happened or not. And we got to 60%, approximately.
But how are
58.
you selecting? So I mean, of the many things that could have followed later and so on.
I just asked him in the following 3 months whether it happened or not. Because the experiments were done in 2000, we took news data from 2010, and we're asking people in late 2010 what had happened since it happened, let's say, from the news title till now. Not perfect, but yes. Maybe it's going to happen in the future, but this is the experiment methodology we tried.
And so the missing 20% implies the cases where they just couldn't, it couldn't look at the anything.
Yeah, well, they said, well, we're not certain, we're not sure. Well, I couldn't find it, right? By the way, the things that the algorithm got wrong, the predictions look okay, but for example, there was a story about somebody coming into a synagogue and shooting people. So the algorithm, a trial will be held. Well, makes sense, right? But the only problem that it missed one really important feature, that the person was 85, and he died before the trial. Okay, so this is like things that the algorithm got wrong. Okay, so yes.
So if I have a down algorithm, basically just say that whatever you say, also say that the sun comes up from the east. That's like predicting get all the bits.
So this is why we did the experiment of asking people how, whether the cause and effect actually makes sense.
So that would be the previous chart.
Yes,
Okay.
this is what I showed before.
But
And this is checking whether it's happened or not.
Okay, but for that dumb system, you get 100%.
Yes.
Correct.
Yes. If you say something was wrong, but then in the other experiment you
You
will
get
get.
very low score.
Yes. So think about like recall precision. And because I have 5 minutes, I want to talk about the limitation of this system. Okay, so the only problem that, as I said in the beginning, it trains on positive examples. It has no negative examples. So overgeneralization is a problem. Okay, so for example, I had problems of lightning killed 5 people. The algorithm says lightning goes to jail. Well, of course, if you never saw a natural disaster killing somebody, it says it doesn't go. So the first problem to solve is actually maybe giving more examples. And what happened is we were going on very precise way of getting cause and effect by the way we're extracting, because we're using patterns predefined. So maybe even going like not with predefined templates, and maybe somehow extracting using temporal correlation, cause and effect. You can get, maybe it's gonna make the algorithm more, I don't know, prone to mistakes, but then it's gonna have more examples, it's not gonna overgeneralize. Okay, and again, as you said, like, how do you actually evaluate this kind of systems? Okay, so first of all, how can you automatically, without humans, check whether something happened or not? Well, it can happen like in 5 years from now, right? How do you know? Okay, but the way I see it from here is, first of all, there's an interesting way of getting world knowledge and inference from what we are actually writing. And what I enjoyed here was going from text to reality and trying to get to a level. I'm not talking even about an expert. I'm talking about the thing that going from at least as well as humans do. Understanding even the most common things that we do. So I'm going to finish with showing like some examples. Okay. So there, let's say sometimes wheat prices will fall for China overtakes Germany as world's biggest exporter. So it saw in the past in World War II that there was a crisis between Germany and France. Okay, and now France is #1 and sees that production of one of those countries actually falls. Okay, so the question is, one, how can you use the different time correlation that we have between things and do even things that are not only things that humans think are logical? How do we know, for example, that for 2 Palestinians reportedly shot dead by Israeli troops, a war will not be waged? Just because we saw it once in the past doesn't mean it's going to happen now. How do we take the entire context of events and actually enter all this into the system? And how do we actually build more interesting features on that? Okay, so how do we handle examples like this guy was 85 and he would not be trialed, right? So we can say it as a joke between us, he's so old, he's not going to be judged. How do we know all this? So one way would actually to look at the text, right? So currently we're focusing on new status because it's an easier NLP task. How can I actually start with an entire text as well? And I think that's it.